Welcome to the Excel Modeling Basics section of this Beyond Formulas Excel Modeling training series. In this advanced lesson, we're going to learn how to use macros and VBA coding to create your own user-defined formulas. It's really not that hard, but if you feel this is beyond you, you're welcome to skip this lesson and go on to the next one. The goals of this lesson are to teach you about the Visual Basic Editor and how to use it to create macros, subroutines, and functions. To teach you the basics of creating and editing macros for automation. To teach you the basics of creating functions so that you can turn any mathematical algorithm you like into a user-defined function in your model, useful when Excel doesn't have a built-in formula that does what you need. For this lesson, you will need the 6.4 Modeling User-Defined Formulas starter file. By the end of this video, you'll have created 3 of your own user-defined functions using Visual Basic, which will combine a set of inputs you designed to create the continuous S, fast growth, and slow growth curves. But before we start, let's get to know the Visual Basic Editor. Go into Excel now and open up the 6.4 Modeling User-Defined Formulas starter file, and then go to the Adoption Curve tab. At the top, you'll see the simple linear interpolation-based adoption model we created earlier. We're now going to recreate this using our custom function instead. To open up the Visual Basic Editor, you can either use a shortcut, Alt and F11, or you can access it using the Developer tab. To view the tab, you'll need to go to File, Options, click on the Customize Ribbon option on the left-hand side, and tick the Developer tab. Hit OK, and notice that the Developer tab has now been added above. Clicking on it gives you a range of options relating to Visual Basic and other tools we'll cover in the upcoming lessons. To go to the Visual Basic Editor, click on the Visual Basic icon on the left-hand side. Now that you're in Visual Basic, a couple of key elements stand out. The middle one is the code window, which is where you'll be composing your coding masterpiece. On the left-hand side, you'll see the project management drawer, made up of all your worksheets, hierarchically stacked within the file you're currently working in. Any code you write must have a scope, that is, the document to which it's going to apply. If you type your code into any one of these individual files, then that code will only be applicable and only be callable by functions in that sheet. If you'd like your code to be accessible across all sheets within your workbook, you have to create a new module. To do so, click on the Insert menu above, and then click on New Module. Notice that a new Modules folder has been added to the workbook we're looking at, and a Module 1 file has been added. Any code in this module will be accessible by all of the worksheets throughout your model, and hence will be where we will be entering our code. But what is this code I keep speaking of? It's a series of instructions we're going to provide Excel that Excel will carry out every time this particular function or subroutine is run. The 2 ways to generate code are to either type it yourself or to record a macro, which converts steps that you take in Excel into the underlying code steps required to reproduce those results. There are 2 types of code structures that you're going to care about. A subroutine is a set of instructions that VBA tries to replicate each time the sub is triggered. The purpose of them is to automate repetitive tasks to save you time. In my experience, they are rarely that useful, although I have used them to create the Excel shortcut game, for example. Macros are typically a version of subroutines. They perform a set of predetermined steps and can be called using buttons or shortcut keys. You can easily record any steps you take in Excel using the Record Macro feature. Let's go ahead and do that now. Starting in our Adoption Curve tab, and going into the Developer ribbon above, hit the Record Macro button. This will trigger a dialog that asks you to name a few things. Let's call this one 10 steps. And we can create the shortcut key Control, Shift, and T. We want to store the macro in this workbook, and we can give it a description, adding 10 consecutive digits to sequential columns when triggered. Hitting OK begins the recorder. From wherever we are in the active cell, we now want to add 10 consecutive digits. Excel has already recorded every one of these steps, so let's stop the recording and go and have a look at the code created. Let's go back into the Visual Basic Editor now. Notice how Excel has automatically created a second module into which it's inserted the macro code. You can see the subroutine, denoted sub, is called 10 steps as we had labeled it. It includes the description, the keyboard shortcut, and all of the steps we took. Notice how it started off at whatever active cell was available at the time, added the value 1, and then selected specific new cells, adding the respective value each time. Let's go back to Excel and see how it works. I can delete all the values I previously created, move my mouse anywhere, and hit Ctrl, Shift, and T. Notice how Excel did something strange. It used the cell that was currently selected, adds the value 1, and then follows the instructions, going to each specific named cell and then entering the value and then going on to the next one. Take care when recording macros this way in Excel, since it tends to be very literal with exactly what it records. In this case, because I didn't select a specific cell before I started to input the number 1, it merely assumed it should input the number 1 into whichever cell is currently selected. Let's go into the code to clean some of this up. Presumably, our intention was to create 10 consecutive numbers in consecutive columns based on wherever the current starting point is, rather than defining specific cells in which to enter the values. Let's go ahead and do this now. Start by deleting all the code that has been created by the macro. Instead of writing out each step to take, we can use VBA's for next loop. The structure of this loop starts off with the for statement, for I equals 1 to 10, followed by the action that you'd like to repeat, and ending with next I. In this example, I is a random variable only used within the construct of the subroutine. It gets generated the first time it runs as 1, then executes all the code in the loop, in this case just this one active cell formula command, and when it gets to the next I, it increments the I from 1 to 2, and it keeps on going until I equals 10. The next thing we need to do is update the reference. So we want to say from the cell that is currently active, i.e. active cell, we want to offset, which is a very similar term you've used as an Excel formula, and then we want to offset 0 rows, and we want to start in the current cell as the first one, so that's I minus 1, and then as I is incremented, we want to offset more and more columns off to the right hand side. Lastly, we want to say that the value of that cell must equal to I. So this very simple coding structure now replicates exactly what we tried to record in the macro, but we'll use whichever cell I currently have selected and then add the values 1 to 10 to all subsequent cells. Let's go give it a try now. Let's go back into Excel, select a random cell, and hit Ctrl, Shift, T. Notice how the values 1 to 10 have automatically been added to all subsequent cells. You can learn everything you need to learn about VBA and about macros by taking a specialized VBA and macro course, but hopefully this basic introduction should give you a little bit to work with. The more powerful thing I think that you can do with VBA is create custom user-defined functions. Let's go learn about those now. Functions are similar in some ways to macros, with one major difference. Their purpose is to take a series of inputs and come up with a single output, much like the sum or VLOOKUP formulas do. User-defined functions are what you use when Excel doesn't have a function that does what you want. Let's say you want to create a function that returns the absolute value of the difference between any two figures. Well, you can start by typing function and adding the function name that you'd like to create. I will call my function absolute difference. Next, you'll want to define all of the inputs for your function. Here, we'll say first number as double, where double is a data type that can contain anything from integers to really large real numbers, and second number also as a double. There are a host of other data types that you can assign to any of your variables, including string, integer, date, etc. Now, since the purpose of a function is to define a single output, we also want to define the data type of that output. Here, we'll say that the data type should also be a double, since the interaction of a double and a double will likely be a double. Then we want to get into some of the logic of our function. Let's say that if the first number is greater than the second number, then the result should be the first number minus the second number. But if the first number is less than the second number, then the result should be the second number less the first number. That's it for the logic. We finish up our function by using the same name, in this case absolute difference, that we used as the function name, and making it equal to the result of our algorithm in the middle. And then we end the function. If you call this function anywhere in your Excel model and pass it two numbers, this function will go into this custom VBA code, use the logic you've defined to create the answer, assign the answer, which is a result, to the function name, and return that in your Excel formula. And so we can use this function approach to create complex adoption curves. For this training, I want a formula that takes a series of inputs and creates a logistics function curve. S-curves, or logistics functions, can be used to model nonlinear progression from one point to another. The logistics curve can follow the familiar S pattern, as shown here. Or, if we play around with the amplitude and the location of it, we can use it to create the slow ramp-up curve or the fast ramp-up curve. Sadly, Excel doesn't come with a built-in logistics function, so we're going to have to create one. You need to understand the math of what you want to create, and understand all of the parameters you need to include in the formula. For a logistics curve, we need a starting point, we need an ending point and time, and we need the value and time of the first inflection point. We actually create the shape by moving a time t progressively along the timeline and then calculating using the model each consequential point s on the curve. So the final parameter we need to pass into the model each time is the current time t to give us the output of the function at each time. Defining our function, we have function adoption s-curve, we have the end value and the end period, we have the first inflection value and the first inflection period, and we have the current period, as discussed. And the result of all of this should be a double. We're then going to add a bunch of code in the middle and finish up with the end function command. Don't worry too much about the complexity of the math. All you need right now is to set up the inputs we've discussed in Excel. On the right hand side, you can see how I've done this in a very simple way, with starting and ending points and the first inflection points for each of the three scenarios I'd like to manage. So let's go into Excel and create this now. Start off by typing all of this code into the VBA code window. Just kidding, we're going to copy it instead. From the VBA window, you're going to go up to the next step-by-step worksheet, where we have already defined this function, ready for you to copy. Select all three rows and hit Ctrl-C, and then go back down to your Module 2 and create the new function by hitting Ctrl-V. But I don't want to make it too easy for you. There's still something wrong with this function. Can you tell what it is? No function is complete until you actually assign the function name to the result of all the code you've created inside. Therefore, in order for this function to actually operate, we need to set the adoption s-curve variable, which is the same as the function name, as equal to result, which is the variable that holds the value calculated by the operation we defined. Now that the function is really complete, we can go and try it out in Excel. We've started by creating the adoption S-curve custom formula. Therefore, go down to cell G38, which corresponds to the first cell within the S-curve scenario row. And let's begin our formula by typing equals and starting to type adoption. Notice how the custom formula we've just defined, adoption S-curve, now appears in the auto-populated list. Select it and hit Tab to autocomplete. Notice that Excel doesn't go the next step to conveniently tell you what inputs your new formula requires. For the purposes of this exercise, I've created this handy little cheat sheet on the bottom left-hand side. The first value we need to input is the end value. In this case, it's 100%. The next one is the end period, which is 20, followed by the first inflection point value, which is 3%, followed by the first inflection point time period, which is 5. And lastly, we want to define the period number for which we'd like the output, which in this case is period 1. Closing brackets completes the formula, but in order to drag this across, we need to go and update our absolute and relative references. We'd like the ending value and ending period to remain constant, so hitting F4 and turning both into complete absolute values is the right thing. And for the following ones, we'd like to be able to drag this formula around, so let's lock the columns. And finally, for the period number, we'd like this to shift as the formula shifts across, so let's lock the row. Hitting enter creates our first value, and if we copy that cell using Ctrl-C and drag it along to the rest of the periods, we should get a brilliant S-curve. Looking at the chart created below, you can see that this has done exactly what we intended. Now that we've completed the S-curve, let's go ahead and complete the slow and fast curves. Introducing your three new curves, slow, fast, and S. The adoption slow curve is going to use exactly the same logistics curve parameters we've just defined, but make some within-algorithm changes to adjust for the amplitude and location of the curve. The fast curve will take the same approach with the same input parameters, but make alternative adjustments to give you the top half of the curve. and the adoption S-curve is the one we've already defined. You can find the corrected code for all of these curves in the start sheet within the VBA code window. Let's go copy them across now. Back in the VBA code editor, we're going to open the start sheet and copy the code from all of the functions we just created by selecting all of the lines, hitting Ctrl+C, and then going back to our module and pasting the new code over the formula we've just created. Now you have the completed code for all three of the new adoption curves. Let's go back into Excel to try them out. In the fast curve, let's start by going into quarter 1, hitting equals, and typing adoption. Notice how all three curves now appear in the auto-completed list. Move down to the adoption fast curve and hit Tab to begin. Remember the values are the end val as the first parameter, the end period as the second, the first inflection value as the third, the first inflection time as the fourth, and the current period as the fifth. Closing the brackets to complete the formula gives us our first value, and copying that formula across to the end should give us our fast adoption curve. Finally, let's copy this formula over to the start cell to finish up. Let's now do the same with the slow curve. Start by hitting equals and typing adoption. Scroll down to the adoption slow curve and hit Tab, and let's complete the formula one last time. Next, you've got to add the same parameters that we did previously. There's the ending value, the ending period, the first inflection value, the first inflection period, and the current period. Closing the formula and copying it across with Ctrl+C and pasting it across the range gives us our third slow curve, which we need to copy the value to the start column of to complete. To round off our adoption scenarios, we can use the forecast formula that you learned previously to create our linear curve. Simply go to the starting point, hit equals and start typing forecast. Hit Tab to autocomplete and begin the formula. The X in this case is the current period. The known Y's are the ranges of values that this forecast can take. Don't forget to hit F4 to apply the absolute references. And the known X's are the ranges of periods that this forecast can take. And again, don't forget to add the absolute references. Complete that formula, copy it using Ctrl+C, and paste it across the rest of the values. I'm going to use the paste options to correct the issues this has created with my formatting by restricting it to paste formulas only, and we're done. Notice that the forecast formula uses the fact that I have a complete range of values to predict and time periods to predict them for, and then uses the current period in each case to linearly predict what the Y value should be, which creates a simple linear curve. And there you have it. We've created an incredibly powerful user-defined function that takes a handful of inputs, applies a very complicated mathematical procedure which Excel doesn't support natively, and creates a beautiful output. This approach is much more powerful than the one that we discussed previously with simple linear interpolation, since we can very easily adjust a small handful of input parameters to create vastly different outcomes. We'll go on to use this custom function feature again, a little later on in this training. Now that we've done all this fancy footwork to create these beautiful adoption curves, we're going to use them in the next lesson to create a phased geographic rollout.